Hi, everybody. I'm Greg Paul, founder of Turing Micro, and I've also got my co-founder, Rob Lundstrom, on the chat. Like Albert Einstein said, we cannot solve our problems with the same thinking we use to create them. And you really got to invent something. Next slide, please. So this is our team. It's made up of XWestern Digital CPU designers in Southern California. Also, our inventor, Bob Patiller, did one of the main original processors on the Xbox. Myself, Rob, and we have a lot of other engineers that we 1099. Next page, please. So there's a problem in the world right now in processing, and Ryan Hatcher, you mentioned a lot of bottlenecks at Lockheed that you're interested in, and Hanko Robotics. I want to show you where we can 5 to 10x the motors and make it easier to program. And Danny Jensen, we have a replacement for the FPGA. Right now, across the bottom of the screen, when you see that there are multiple solutions, multiple processors, and why is that? They have to be hybrided together because they each do some good things, but not everything fast enough or together as one. And why is that? That's because they're batch processing. The I/O gets bottlenecked into 1 or 2 main processors or a couple core processors. And this takes many clock cycles, a lot of hertz. So this also mismatches the processing architecture for the algorithms, and it slows everything down. Kind of like when you make an ASIC, you make it around an algorithm. In a perfect situation, you would have the right architecture for every algorithm and every input. Next slide, please. So what's our solution? It's a decentralized distributed intelligence. What's needed is a processor that can dynamically reconfigure the architecture in 1 clock cycle, a billionth of a second, without a power cycle. And then to unclog that centralized problem of a big processor, you need a core for every input, and this will end the batch processor nightmare. This is something we've solved. Like in a race car, real-time control, upshifting for faster processing, downshifting in the turns. You reconfigure the car, you change the power. We can additionally change the power and voltage in our chip on the fly. Next slide, please. So what have we invented? It's a combination. It's a compiler, which is the intelligence. It's software definable, and it's a chip we want to make. But we can build this in an FPGA to prove it out currently and even accelerate that. Across the bottom, I show you, like on the other pages, GPUs, FPGAs, ASICs, all mixed solutions. Over on the right in blue, you see the new features and why we can replace an FPGA and GPU. 1 clock cycle reconfiguration. The next piece is the magic. We can process on multiple layers of virtual fabric, even with 2D manufacturing. So we can jump in 1 clock cycle, 1 billionth of a second, to another piece of the fabric that processes instantly anywhere. So now it auto maps, it auto timing. Anything C compiled. So now you don't need a high definition language engineer like you need on an FPGA, and dynamically without a power cycle. This also creates a situation of auto masking the power versus time for hackers. We can change the voltage on the fly through a feedback loop. And we're cookie cutter. We can go from IoT to something better than Cerebrus, wafer scale. Next slide. This is just an example. We call it a Rhapsody, a reconfigurable algorithmic pipeline core. Again, jumping layer to layer, assign a core for everyone. We've got a couple patents already. We've been in stealth. It organizes the code, it compresses it, and it removes those bottlenecks. Next slide. So we were just awarded the phase 1. We're looking for phase 2, of course. But this is a comparison of some of those features I just mentioned. When you look at FPGA, GPU, ASIC CPUs, and across the board, we are the real-time supremacy king in a clock cycle. That is the only thing you give up. Everything happens in a clock cycle. It breaks the algorithms down in a clock cycle. It's completely wide and completely flat. This will help robotics, drones, autonomous AI, video streaming, supercomputing, AR, VR, across the board. And it's Turing complete, hence the name Turing Micro. So we can co-process And we can be in an FPGA literally before we are to chip. Next page.
Hey, Greg.
Yes, sir.
Greg, you have a couple more seconds?
Okay. This is where we're headed. Sweet spots from robotics all the way to wafer scale AI. We can click between 4, 5, and 6G, replace, and we can marry any type of compute on the different layers. So this is how we do that real-time supremacy, because we can be mixing things that don't work together today. And finally, last slide, next slide. We wanted to do 2 runs in multi-project wafers and build our compiler in 18 months. Happy to have any questions.
Hey, Greg, this is Dana. I was wondering if you could elaborate. I saw on one of the slides, a couple slides back, that these things are rad hard. Is that intrinsic, or is that something that you've done as an extra step?
We can run MRAM. And MRAM, so we're talking with one of the biggest in the United States. Obviously, there's spin in the UK, but I can't say who we're talking to over on the West Coast. But MRAM. So we can run S, D, or M, and we can be Turing complete and do more than just AI acceleration.
Okay, so it's an intrinsic character of the way you're building the thing then.
Yes, sir. And we can make it more dense than the other pieces because of this as well.
Well, that's one of the other issues we've had in the past, right? I mean, some of these rovers going to Mars are using PowerPC chips, right? Because they might be from the 90s, but at least they're not so elegant that they can't stand a little bit of disruption, from radiation.
We've simplified data movement and compute. And by doing this, we have a more efficient, effective, and then more flexible with all these different features. You're able to solve these bottlenecks.
So if I can just ask one question, I know we're short on time, but I'm interested in the roadmap here for integration in the packaging level.
The one go-to-market slide, if you can pull it up, or go ahead.
Sorry. So I'm curious if you guys are positioning yourselves for chiplet level integration, like system and package level integration. Is that something that, did I miss that?
We're at the simulation right now, which is why we went the grant route for the moment, to do industry standard simulations to show any trade-offs or comparisons for anything you like. But on the go to market slide, keep going. You're going the wrong way. Okay. Second to the last slide. There you go. Go to market. Go back one. Go to market. Okay. So we're going to make simulations, and then we can use anybody like Global Foundries. We're fabless, just like an ARM model, license. But we can prove it today, and we can prove anything you like over the period of this. We can make actually a compiler that is a licensable compiler to accelerate FPGAs, but our chip itself will have our own architecture that we've patented, and obviously give you the best of all worlds. It will integrate into anything you're doing. It's Turing complete. It can co-process or run it all itself.
Gotcha. Okay, thank you.